Okay guys, in this video we are going to be talking about the empirical gas laws. And what the gas laws do is they express relationships between the gas variables. And so these are the gas pressure, the volume, number of moles, and the temperature of the gas. And so we have a number of laws that are named after different people, and they all involve keeping at least one or, and more commonly, two of the gas variables constant, and then looking at how the other gas variables relate to one another. So for example, in Boyle's law, the number of moles of gas and the temperature of the gas are held fixed, and one finds that the pressure is inversely proportional to the volume of the gas. So as the volume gets larger, the pressure gets smaller. As the volume gets smaller, the pressure gets larger, which is fairly intuitive if you think about it. This proportionality relationship can be expressed as an equation like this, where the 1 refers to the initial state of the gas and 2 refers to the final state of the gas. So if you have a change in, for example, the volume of the gas, and if you know the initial pressure and you know the initial volume and the final volume, you can then use this equation to calculate the final pressure. For Charles' law, for constant number of moles of gas and constant pressure, you find that the volume is directly proportional to temperature. As temperature increases, volume increases. As temperature decreases, volume decreases. And that leads to this equation relating the initial volume and temperature of a gas to its final volume and temperature of the gas. In Gay-Lussac's law, which is also called Hamilton's law, the number of moles of gas in the volume is fixed. There you find that the pressure is directly proportional to the temperature. Higher temperature means higher pressure. Lower temperature means lower pressure. And you get this law here, or this equation here, relating pressure to temperature for a change in state. The combination of these laws is expressed here. Here, the only thing that is fixed is the number of moles of gas in the combined gas law, and you get this more complicated expression where you have 6 quantities that can be changing, and given any 5 of the variables, you can always find the 6th variable. In Avogadro's law, pressure and temperature are fixed, and one finds that the volume of gas under those conditions is proportional to the number of moles. So more moles of gas means larger volume, fewer moles of gas means a smaller volume, and that leads to this expression. So you need to be able to work with these different equations given, for example, in Boyle's law, given any 3 of the variables, you need to be able to find the 4th. And they all work in the same way. You just need to be able to keep the laws straight. Here are some figures illustrating Boyle's law. So in this device here, you've got a syringe where you've got some gas in it. And if you squeeze the syringe, it's going to cause the pressure to go up. If you pull the syringe out, it's going to cause the gas pressure inside to go down. And if you were to monitor the pressure as a function of the volume of gas, it would map out a curve like this hyperbola. And as you increase the volume, you see that the pressure goes down. As you squeeze the volume, you go to smaller and smaller volumes, you see the pressure goes up. Okay, so that's Boyle's law. This slide is more or less the same. It has a couple of, it has a term down here at the bottom, the compressibility. So gases are compressible fluids, which means you can squeeze them into smaller and smaller volumes, unlike liquids, which are incompressible fluids. If you squeeze a real gas long enough or hard enough, you get it to a small enough volume, what you'll find for low temperatures, you'll find that gas will condense to form a liquid. But when the gas is in the gaseous state, you'll find that it more or less follows Boyle's law to some extent. This is a typical Boyle's law problem. Okay, we've got a volume of air occupying 12 liters at 98.9 kilopascals. That gas is compressed to a higher pressure. Temperature is constant. It's assumed that the number of moles is constant. What is the new volume of the gas? So you would use your Boyle's law formula. We're solving for the new volume. The initial pressure was 98.9 kilopascals. Divide that by 119 kilopascals. Multiply that by the initial volume. Run that through your calculator. I'm getting 9.97 cubic decimeters. As my answer. This problem is identical to this one in every way. The only thing that's different are the numbers that you plug in. Okay, so try this one on your own as an exercise. And I'm going to turn to Charles' law, but I need to point out that there is a I wanted to point out that these are the incorrect graphics for Charles' law. In fact, these are the graphics for Gay-Lussac's law or Hamilton's law. But the text, however, is correct for Charles' law. So we're going to ignore these figures in this table, and I'm just going to make a new figure. So what I'm going to plot here is volume of gas as a function of temperature, and let's go ahead and use degrees Celsius. So let's imagine that we're doing, we've got gas at constant pressure, and what we're doing is we're cooling the gas and we're measuring the volume that it occupies. And so what we'd find is we'd start collecting data points that do this. They go down linearly, so the volume is linearly going to get smaller as we decrease the temperature of the gas. And let's suppose this is the coldest temperature that we can make. Okay, we can't get any colder than that. If you extrapolate the line down, what you'll find is that the line intersects the axis at minus 273.15 degrees Celsius. Okay, it goes to zero volume at that temperature if you extrapolate the line. And so this we call absolute zero. It does not make sense to have a volume less than zero, and so this is taken to be the lowest temperature that can be achieved. We typically use the Kelvin temperature scale, where instead of where absolute zero occurs at 0 Kelvin. And so we've done these temperature conversions in I guess the first chapter. And so these are going to come into play whenever you're doing gas law problems involving temperature. You always need to express your temperature in units of Kelvin. So we always have to be ready to convert degrees Celsius to degrees Kelvin. Here are the equations that we've already looked at for Charles' law. And so I'm just going to move on to the Charles' law problem. And so here's an example of that. So we have a sample of gas that's at 1 atmosphere and 21 degrees Celsius, and its volume is 785 liters. What would be the volume if this temperature had been 28 degrees Celsius? So we need to use the Charles' law formula. which looks like this. We know the initial volume and the initial temperature. We know the final temperature. They want us to find the final volume. And so we need to solve for V2. Just doing the algebra like this. Now before we rush to putting in numbers, we need to convert these temperatures to Kelvin. So the final temperature of 28 degrees, we need to add 273. So that's going to be 301 in the denominator. And T1, which is 21 degrees Celsius, we need to add 273, 294 Kelvin. And then for the volume, we'll multiply by that 785 liters. Run these numbers through your calculator. And I'm getting 804 liters out of that. Okay, so this illustrates a calculation involving Charles' law. I think you're going to find that this problem is identical. You're given a volume of oxygen gas at 19 degrees Celsius, and they want you to calculate the volume at 25 degrees Celsius at the same pressure. Okay, and so since pressure is constant and it's implied that the number of moles of gas is constant, this is a Charles' law problem, and so you would use this exact same approach to calculate the answer. Well, here I just have a list of the other gas laws. Okay, we've already looked at their equations on the first slide in this video. And so let's just see what we have next here. Okay, I think I have one or two more concepts before we do some more problems. The term standard temperature and pressure is often used in gas law problems. Note that it's not the same thing as the standard state that we talked about in thermochemistry. It's a different idea. In gas law problems, standard temperature and pressure is 0 degrees Celsius and 1 atmosphere pressure. In thermochemistry, there's technically no standard temperature, but most thermochemistry data is tabulated at 298 Kelvin. Okay, so they're not the same temperature typically that you're talking about. So try to keep that straight. This STP, standard temperature pressure, it's not quite the same thing as standard state in thermochemistry. At standard temperature and pressure, all gases have about the same volume per mole. It's about 22.41 liters per mole, give or take. And so that's what we call the molar volume. So the volume per mole of gas, it depends on temperature and pressure, but seems to be independent of gas type. Okay, that's going to be what we call the ideal gas, or one of the features of the ideal gas, which we'll probably get to in the next video. For now, we're going to do several problems. Okay, so here we're talking about a can of hairspray. Okay. On the can, there's a warning: store only at temperatures below 48.8 degrees Celsius. Do not incinerate. Why would they put that kind of warning on a can of hairspray? Well, as you probably know, it contains compressed gas in it, and pressure is proportional to temperature. This is Gay-Lussac's law. So if you increase the temperature of the hairspray can, the temperature of the gas is going to go up, the pressure is going to go up. It might explode, it could spark, and it could ignite the isobutane gas, causing an explosion, which would be very dangerous. So that's why you don't incinerate flammable gas containers. Here we've got a little numerical problem. The can of gas is initially at 24 degrees Celsius and 360 kilopascals. It has a volume of 350 milliliters. If the can is left in a car that reaches 50 degrees Celsius on a hot day, what is the new pressure of the can? So we can solve this using Gay-Lussac's law. Here's the equation that we'll use. Okay, we know the initial pressure, the initial temperature, the final temperature, and we're being asked to find the final pressure. So we'll solve for P2. Don't forget to convert your temperatures to Kelvin. So taking T2, which is 50 degrees Celsius, so 50 plus 273, 323 Kelvin, divide by the initial temperature, 24 plus 273, 297 Kelvin. Multiply that by the initial pressure, 360 kilopascals. And I'm getting 392 kilopascals for the new pressure. Okay, so that's an illustration of Gay-Lussac's law. Here we've got a sample of nitrogen gas that has a volume of 45 milliliters at 27 degrees Celsius and 600 torr. What pressure will it have if it's cooled down to minus 73 degrees Celsius and the volume remains constant? Well, here we're lowering the temperature, so you would expect the pressure to drop. Now, this is also a Gay-Lussac's law problem, and so it involves the same setup. The only thing that's different are the numbers. And so I'm going to let you go ahead and work that problem as an exercise for yourself. And let's take a look at some of these questions. So here we've got a balloon. It's got 5.41 liters of helium, 24 degrees Celsius, and the pressure is 101.5 kilopascals. Suppose that the gas in the balloon is heated to 35 degrees Celsius, so the temperature is changing. And then the pressure also changes, 102.8 kilopascals. And then they want to know what's the volume of gas. So this problem is an example of the combined gas law. So both pressure, volume, and temperature are changing. And so we need to use this equation and solve for the final volume is what they want to know. So we need to solve for V2. So V2 is going to be P1 over P2, T2 over T1, times the initial volume. So I've just algebraically rearranged this equation and solved for the unknown volume. And now we're going to plug in the numbers, and we need to be careful with our temperatures. We need to convert those to Kelvin before we do the calculation. So the initial pressure, 101.5 kilopascals. Final pressure, 102.8. Now we need the final temperature. Okay, the final temperature was 35 degrees Celsius, so 35 plus 273 gives us 308 Kelvin in the numerator. And then the initial temperature in the denominator, 24 plus 273 is 297. And then times the initial volume, 5.41 cubic decimeters. Run these numbers through our calculator. I'm getting 5.54 cubic decimeters. So this is an example illustrating the combined gas law. I want to do one more combined gas law problem. I want to do part B because this is an example of a combined gas law problem where you do the calculation symbolically. So take a look at part B. Suppose you have a sample of gas with a pressure of 2 atmospheres. What will be the new pressure if you increase the temperature by 3 times and decrease the volume by 1/2? Okay, so it is a combined gas law problem. Right? Pressure, volume, and temperature are changing. And they want to know what is the final pressure. So they're asking you to solve for P2. So we can algebraically set that up. P2 is going to be P1 times V1 over V2 and T2 over T1. Okay, so that's the algebra. But all we know is P1, right? They haven't given us any of the other numbers. Well, what you need to do is read the problem carefully and realize what they're telling you is that T2 equals 3 times T1 and volume 2 equals 1/2 times volume 1. So they've given you this extra information which you can substitute into the equation. Okay, so I'm going to take these equations and substitute them in. P2 equals P1, V1 in top, and then it's 1/2 V1 down below. That's V2. And then T2 is 3 times T1 divided by T1. Notice that the quantities that we don't know cancel out. And so we wind up with, this is going to be 6 times P1. Since P1 is 2 atmospheres, it's going to be 12 atmospheres is the answer. Okay, so this is an example where you're being asked to do the combined gas law problem symbolically. And so you want to watch out for those types of problems. This is a conceptual problem. Okay. So we've got 3 flasks, each have a volume of 3 liters, and they're each at a pressure of 878 millimeters of mercury. One flask contains helium, the other one contains argon, and one contains xenon. Right. So here I'll just draw a picture. Here's our 3 flasks. They all have the same volume, despite my drawing. Helium, argon, and xenon. Okay, which of the flasks contains the most atoms of gas? It's a trick question. We are using Avogadro's law in this problem. Pressure and temperature are implied to be the same. Volume is proportional to the number of moles of gas, which is proportional to the number of atoms of gas. And so if each of the containers has the same pressure, temperature, and volume, then they each have the same number of moles, and they each have the same number of atoms. So part A is a trick question. None of the flasks have more atoms of gas than the other. Which of the flasks has the greatest density of gas? Well, density, whether you use so here's rho for density, is going to be the mass of the gas divided by the volume. Well, each of the gases has the same volume, so the denominator is the same for all of them. However, the numerator is the mass, which is going to be, the number of moles of gas times the molar mass. Right? You could write it like this: number of moles times the molar mass divided by the volume. Well, each gas has the same number of moles and the same volume, but they have different molar masses. the xenon has a larger molar mass than the other two gases. Therefore, the xenon is going to have a higher density than the other two. Okay, so the answer to part B is the xenon. If the helium flask were heated and the argon flask were cooled, which of these three flasks would be at the highest pressure? Here we're going back to Gay-Lussac's law. Pressure is proportional to temperature for constant volume and number of moles of gas. So the one that has the highest temperature, which would be the helium in part C, it would have the highest pressure. So the answer to part C would be the helium, which has been heated up. Part D. Say the temperature of the helium was lowered while that of the xenon was raised. Which of the three flasks would have the greatest number of moles of gas? Another trick question. We haven't changed the number of moles of gas at all. We've just simply heated up the gas or cooled it down. And so that's not going to have any impact on the number of moles of gas inside the container, as long as it's sealed. Okay, so part D is a trick question. Well, I am going to go ahead and stop this video right here, and we'll start talking about the ideal gas law in the next one.